Hello everyone. So till now from module 2 we have completed studying about common source amplifier with and without source resistance and source follower, which forms the first part of the module 2. The second part is MOSFET internal capacitances and high frequency model. First we'll study about the internal capacitances in the MOSFET. So under this we have gate capacitive effect and the source body and the drain body depletion layer capacitances. The internal capacitances are mainly due to the two listed. So before moving on, we need to have a basic understanding where the capacitances or where actually in which junction or which between which terminals the capacitances are present. So this is the MOSFET and MOSFET with the basic three terminals, that is gate, drain and the source. So a capacitance between gate and the drain, that is CGD, is present. A capacitance CGS is present between gate and source, and the capacitance between CDS is present between drain and the source terminal. So in this way the capacitances are present between the three terminals. Okay, and first let's study about the gate capacitive effect. So why these capacitances are present? The reason behind the formation of a capacitor in the MOSFET structure, let's understand. The polysilicon that is present over here will form a parallel plate capacitor with a channel. The polysilicon is present here, okay, below the metal. This and the channel is formed here, okay. Now we can see the polysilicon is parallel to the channel that will be formed. So in between that we have oxide. So the polysilicon and the channel that are parallel will form a parallel plate capacitor with the oxide layer serving as the capacitor dielectric present in between the two. Okay. So in this way the capacitor is formed in the model of the MOSFET, and this capacitance is denoted as Cox, that is measured per unit area. Okay, and next we have capacitances between the source and the drain. To the body. So the source will form a capacitance with the body, and the drain will form a capacitance with the body. Here the source is of N type dot and body is of P type. Drain is also of N type. So here the capacitances of the reverse bias junction. Source will form with body, drain will form with body. Okay. So the capacitances of reverse bias PN junction of will be formed by N plus source region, which is also called source diffusion, and P type substrate. Second one is N plus drain region will form a capacitor between with P type substrate, that is denoted as CDP. So overall, so these two capacitances and these three capacitances, in total there will be 5 capacitances in the model of the MOSFET. Next, this is general. Internally there will be many. Next we have the modeling of the gate capacitive effect. So first, as soon as the transistor is turned on, the input voltage will rise from 0 to higher values gradually. So whenever the input voltage VDS is very small, the MOSFET will be operating in the triode region, isn't it? So in this triode region, the channel will be formed of uniform depth. Say the channel is formed here like this with the uniform depth at the source as well as the drain. So the gate channel capacitance is of the value WL into Cox. So this capacitance, gate channel capacitance, is divided equally between the source and the drain since the channel is of uniform depth overall. So the CGS and CGD in this case will be equal to half of the gate capacitance, the gate channel capacitance, that is equal to WL into Cox. So in this triode region, CGS and CGD is so much. Next, As and when the input voltage VDS is increased, the MOSFET will be operating in saturation region. So in saturation region, what happens is the channel will be pinched off at the drain terminal and is tapered. Okay, the length of the channel decreases. Okay, previously it was from the drain into the source, and now in saturation region the channel is pinched off and tapered, so the length of the channel decreases. So whatever the gate channel capacitance is present, it will be of 2 by it will be of 2 by 3 WL into Cox. Okay, so this WL 2 by 3 WL Cox is completely dedicated to the source terminal. It is completely assigned to the source terminal. Zero capacitance is dedicated to drain terminal because there is no channel present at all near the gate terminal. So we have CGS is equal to 2 by 3 WLCox and CGT is equal to 0. So this is about saturation region. Next, in cutoff region, the channel won't be present at all. So CGS is equal to CGT is equal to 0. Okay, but the modeling can be done by assigning the gate channel capacitance to the body. So CGB will be equal to WL Cox in the cutoff region. You don't assign it to source or drain, you'll assign it to body in cutoff region. So CGB is equal to WL Cox and CGS and CGT will be equal to 0 because channel is not present. So for all these equations, a small capacitive component must be added for CGS and CGT. Okay, this is because of the fact that this oxide layer forms a junction with drain and source over a small region. See here, in this region, the small region, there is a junction between the source, drain and the oxide. So due to this, a small capacitive component must be added. The oxide layer is slightly exceeding or coming into the source and the drain region. So that's the reason we need to add some small amount of additional capacitance. So this small amount of additional capacitance is indicated as overlap capacitance if the length for which the overlapping is denoted as LOV. This length is denoted as LOV, and here this is denoted as LOV. So COV will be equal to W LOV into Cox. So typically this LOV will be equal to 0.05 to 0.1 times L. And next we have junction capacitances. So this is formed between the source and the body. It is due to the reverse bias PN junctions. Okay, so direct formula is given. So you need to remember this. CSB is equal to CSB naught by square root of 1 plus VSB by V naught. The CSB naught is the value of CSB at zero body source bias, whereas this V naught is the junction built-in voltage, which is typically of 0.6 to 0.8 volt, and VSB is the magnitude of reverse bias voltage. And here CDB is equal to CDB naught by 1 square root of 1 plus VDB by V naught, where CDB naught is the value of CDB at zero reverse bias voltage, and this VDB is the magnitude of reverse bias voltage. And we know V naught is the junction built-in voltage. And next we have a problem to solve, wherein for a N-channel MOSFET with the thickness of the oxide equal to 10 nanometer and length is equal to 1 micrometer, width is equal to 10 micrometer, overlapped length is equal to 0.05 micrometer, CSB naught is equal to CDB, which is equal to CSV is equal to CDV, that is equal to 10 femtofarad, and V0 is equal to 0.6 volt, VSB is equal to 1 volt, and VDS is equal to 2 volt. We should calculate the capacitances COX, COV, CGS, CGD, CSV, and CDV. All the for all the capacitances, the formula is known by the previous study. One thing is, first we need to find out COX. How do we find out COX? COX is equal to epsilon ox by Tox. So this epsilon ox, we know that it is equal to 3.45 into 10 power minus 11. Substitute the value. Then T ox is given as 10 nanometers. Substitute it. We'll get C ox is equal to so much. After finding C ox, it's very easy to find all the other rest of the capacitances. Formula is already given. Just substitute the values and calculate. So this is about the internal capacitances. Next, in the next session, we'll study about the high frequency model.